To be able to determine the drivers of urban growth, the usual linear regression would not suffice because of several factors. The first one is that the population is highly correlated with its previous values. Say the 2015 population for province A is highly dependent on its 2010 value. Thus, we need to account for the temporal effect or the effect of the previous values. Secondly, the growth of one area is most likely also affected by its neighboring areas, and this is the reason why it is important to take into account the spatial effect in the model that we have used. Another thing is that we could view this regression model where the drivers are inputs in a production process and the resulting output is the increase in the population of an area. But simply doing this might lead to misleading results. Because in reality, even if we supply the same value of outputs to two areas, it may be the case that they would yield different magnitudes in their output, which is the increase in the population in this case. The difference in the resulting output, even if we use the same amount of input, could be attributed to the efficiency of that area. With this in mind, aside from the input-output relationship, we also considered estimating and accounting for what we call the technical efficiency in this model. This is called the production frontier model. Here, y sub I represents the scalar output of the producer, which is our case, the provinces. And then we have here x sub I, which is the vector of inputs used by the producer or province I. F of x sub I beta is the production frontier to be estimated with beta as the vector of technology parameters to be estimated, which is just like the right-hand side of a simple linear regression. Meanwhile, TE sub I is the output-oriented technical efficiency of producer I. From this equation, we could see that T sub I could only reach its maximum, which is equal to 1, if and only if the observed output attains the maximum output that would be produced by the function f of x sub I beta. Factoring the random shocks of production, here we have v sub I, which affects having the technical efficiency being less than 1. Here, it provides a measure of shortfall of the observed output from the maximum feasible output in an environment characterized by the exponential form of V sub I, which could vary across producers. Stochastic frontier models provide an improvement in the earlier production frontier estimation procedure as it allows for the impact of shocks on output in the estimates. Production shocks include variation in labor and machine performance, the volatility in weather conditions, or just plain luck that render a producer to obtain a higher or lower level of output, which could also be represented in our case. Over time, the producers get to realize their failure to adopt efficient technologies and correct it soon, after which more efficient production process is applied. Many stochastic frontier models for panel data fail to account for temporal dependencies, which means there should be an improving learning curve of producers, and spatial externalities, which is the adoption of efficiency-enhancing technologies among producers in a spatial neighborhood. Say in our example, if one province is developing, then most likely it would be copied or the myth. Ignoring this aspect of the information contained in the panel data will result to inadequate differentiation of the producer's efficiency-inducing potential, hence may result to inferior estimates of technical efficiency coefficients. So applying this spatiotemporal stochastic frontier model in our setup, we view the provinces as the producers, where the quantity of product, which are the individuals, or the growth in the population that was produced are affected by the given factors of population growth. Other variables were considered as indicated in the literature of population growth, but these variables were the ones who were significant during the modeling procedure. We have ERA, average provincial family income, expenditure, area of province with high hazard to flooding, presence of ecozones, distance to the nearest airport, groundwater allocation, and area. And here is a segment of the results of the spatiotemporal stochastic frontier model, where here we have the effects of each of the drivers of urban growth that were found to be significant. So here in our example, we will just simplify the spatiotemporal stochastic frontier model that we have discussed. We have removed here the spatial and the temporal effect of the model to simplify the discussion. To account for the spatial effect, you just need to add the distance matrix, which is just the distance between provinces, and include this in this model. And to account for the temporal effect, then that would be a more complicated situation since we will be using other packages to account for autocorrelation and other time series components. So here we have the object called train, which could be run or saved by using the function read.csv. As you could see here, the read.csv is followed by the function file.choose. If you do this option, if you run this line, you would see that there would be a pop-up menu where you could select the CSV file that we will be using. The CSV file that we will be using could be found in our Canvas website. So after selecting the working file that we have, we could run this second line, which would allow us to view the dataset that we've exported. So once we have loaded the data using the read.csv function, then we could view the data using this view function. As here you could see the name of the provinces and then the other variables that we have tried to use to compute for. Next, to run the stochastic frontier model, we need to install a package called Frontier. Please take note that this line is required to be run for just a single session. Meaning, if you have already installed the Frontier package, it's already stored in your package tab. So you don't need to run this line every time that you would try to do stochastic frontier model. So if you already have the package here, then we could just load the frontier package by using the function library, then frontier, or check the frontier in this package tab. As you can see, there's stochastic frontier analysis. I will just check this, and this would load the frontier package. After loading the frontier package, we could now use the SFA function. So as we've discussed in linear regression, we have used the function called LM to do a linear model. So here we will just be using SFA, that would stand for stochastic frontier analysis. So here, our y is log house, which is the number of households in that area or per area. And then here are our pre-selected significant covariates. Please take note that you would need to try running this several times to look for just the most or the significant variables that should be included in the stochastic frontier model. Also, a thing that you should take note is that when we are running the stochastic frontier model, we shouldn't just use the actual values of the variables since they are quite different in terms of the magnitude. See, for example, we have the era, which is quite a large number compared to, say, the distance of the nearest airport to that province. So for this to be quite similar to each other, we have transformed each of these variables into their log scale or take the natural logarithm. So if we run the SFA function here and call the result SFM, Then we could now run the summary, and you will see that there would be a result of the SFM with the corresponding coefficients. As you could see here, if we run the SFM, this would produce the estimates of each of the factors. Please take note that this is quite different from the results that we had in our previous presentation. The main difference is that we didn't account for the spatial and the temporal effect in this example. Thank you very much for watching this part of Module 2. Please proceed to the next video for the last part of Module 2.